Okay, hi everyone, welcome to the Oxford seminar. This week we're hearing from Matteo, who will be giving us a taste of quantitative logic.
Yes, thank you, Jason. Hi, everyone. This is a very hastily prepared talk, but I hope I can give you a taste of quantitative logic, which is, as I was saying before, half of my day job. Um, so I want to start first by making a point, which is what is quantitative logic exactly? Because there is a lot of quantitative logic around lately. Quantitative logic in the form of fuzzy logic has been around for a long, long time, since the 70s at least. Um, but there's like a billion different things, right? And I in this last year and a half working on this, I came to a very specific opinion about what is quantitative logic, which, and this is not to flatter myself, but it's just like, oh, actually, there's some credence to this opinion. Lawvere shares in this foundational paper he wrote on generalized logics, which basically quantitative logic should be logic enriched in R, which from a syntactical point of view means that your judgments are going to be valued in R. Okay. So specifically, quantitative logic is going to be a logic exactly like the kind of logic that we're used to, especially when it comes to proof calculi and the theory. Except we are working with what I call an alephic theory, so a theory of true values, which is not the classical one, the binary one. And this is not a change in semantics, okay, like you might have for intermediate logics, for example. So these logics are not quite intuitionistic, not quite classical, like Yukasevich and other like fuzzy quote unquote logics. Those are multi-valued logic. They change the true values semantically. They don't change the true value at the logical level. Okay, so there's still logic in which things are either true or false. Okay.
Is the meta level, so
Yeah,
the level of judgments, either you have judged it so or not.
exactly, precisely. So there's a little subtlety which is not very apparent. I think if you're not a category theorist, probably even less, because in category theory it is really clear, right? Because when you build the models of this logic, you build like a categorical model, for example, then it's clear that you're choosing to use SAT as a base of enrichment, which means that your judgments are going to be sets of proofs, right? Or if you choose the Booleans, it means that your judgment is going to be Booleans. Now, if you choose R, it means your judgments are going to be real numbers, okay? Really easy. So apparently the plan is very clear. Do logic, change the enrichment base, profit, right? Um, in practice, not that easy, but it is easier than I think you might expect, given the lack of such an approach in the literature so far. So I'm gonna start by telling you about this Levy theory. Okay, so what is the true values that we're gonna use at the meta level? It's the multiplicative reals. Um, by the multiplicative reals, I mean a very specific structure that I put on the positive reals, the extended positive reals. Okay, so we take all the reals from 0 to infinity with extremes. Okay, and we give this kind of, I want you to think about linear logic when you look at this table, because that's what I think about. Um, so with the structure that it's given by, so the primary stuff here, and that's why I call them multiplicative, is this choice here. We equip the positive reals with multiplication, the usual one we know, except we need now to make a choice. We need to say what is 0 times infinity, right? There's two plausible choices we can make. 0 times infinity is 0, 0 times infinity is infinity. Uh, and the first like interesting bit of this talk, I think, is to understand that you should actually make both choices and they should give you two different multiplication, right? So the positive multiplication that I call conjunctive multiplication is the choice where 0 times infinity is 0. So it's a kind of conjunction. And the other one resolves it in the opposite way, okay? So you can see this in many ways. I think the way I like the most is that you look at the entirety of the positive reals as a sort of self-symmetric thing. Okay, so 1 is your pivot, and you have a duality that exchanges everything around 1. And so all the structure I'm going to define here is going to be reflected below as a sort of dual thing, right? And so it's natural that when you define multiplication in one way, then you're going to have its precise reflection defining a different multiplication, right? So with this stuff, the positive reals become linearly distributive monoidal poset, okay? And then what you can do is realize there's also a lot more structure, precisely all the structure given by addition, okay? So there's this nice coincidence of terminology that multiplication gives you a multiplicative structure, quote unquote. Addition gives you an additive structure, quote unquote. An interesting bit is that there's a continuum of choices of this structure, all given by basically starting from P, the choice for P equals 1, which is your normal sum, okay? And then conjugating by exponentiation, all right? So A plus BP is equal to A to the P plus B to the P to the 1P. And this is called P sum in real analysis, for example. And then, yeah, the interesting thing about this definition is that as P goes to infinity, we recover the maximum. Okay, so the actual additive in the linear logic sense, and so we see that these connectives sort of form a single generation that is smeared in many different instances that interpolate between, that approximate, or we say soften the hard connective max. Okay. And dually, you have a family of connectives that is given by taking the reciprocals. We call this harmonic P sum. Why? Because for P equals 1, this is harmonic sum, which is a thing. As the name implies, this arises in the, yeah. Well, it comes from harmonic analysis, or like harmonics, as in like the Greek thing. And then it somehow emerges in other fields of science. Yeah.
So this duality between the two rows here is induced. So if you zoom out a little,
Sure.
the full thing, you have on the left-hand side your duality of 1 over A. And so the claim here is that that changes polarity in the sense that the bottom half is always A star connective, B star quantity star of the top half. Is that right?
Like it's a De Morgan duality, if that's the question. As in like everything, like if you conjugate a row with that duality, you get the other row.
Yeah.
Okay. So this is stronger than linearly distributed categories, like a star autonomous monoidal poset. Okay. In the sense that you have these two dual structures, and they are actually dual in the sense there is a duality that from one gives you another, and it's a duality in the sense it's contravariant. Okay. Did I understand your question?
I think so, yeah.
Mhm.
No, in particular, when you make one of these choices for multiplication,
Yeah.
you would find the other one by doing 1 over A tensor 1 over A quantity 1 over.
Correct. Exactly. Precisely. Yeah.
Cool.
And yeah, if you look at what that does on finite numbers, this is precisely what you started with, but on the infinite numbers, like the non-finite numbers, which is fun because 0 is not a finite number in this sense. Do with this whatever you like. Yeah, you get two different things, right? What else I have to say about this? Right, the most important thing for the rest of the talk, or at least for a good part of it, is that, yeah, so these things are still arranged in a way that is let's say, compatible with the usual way that we think about true values. Specifically, unsurprisingly, the multiplicatives distribute over the additives. And this is a very important role in the calculus that we're going to see later. And there's more identities like we've seen that these linearly distribute. There is a much more intricate structure that involves the various often additives.
So what do you mean by linearly distribute?
Oh,
They distribute over each other or what?
it means that a tensor B cotensor C is smaller than a tensor B cotensor C.
Okay.
I don't like the name linearly distributive because it's not a distributivity condition. Yeah, it says that the two tensors commute in a sense, right? That you can do one and then the other or the other way around. But that's the name we're stuck with. I'm starting a movement to call this polar. This is called polar monoidal for reasons because
And they like it not being equal happens with like the zeros and infinities somehow.
oh, so in this case, yeah, in this case, that is just associativity except the zero and infinity, right? In which case you're gonna have on the left, like there's a specific choice of A, B, and C. It's like if A is zero and B and C are infinity or like equivalent choices. Then you see that on top you have zero and on the bottom you have infinity, right?
Right.
So in that case, they are not equal. But in all other cases, it's just associativity of multiplication, right?
I'm not sure if this is the right time to be asking this, but how far can you push the analogy with linear logic? Like, is there an analogous thing to intuitionistic logic here where you have something like taking it slicely?
Yeah, that's a good question. I'll defer this to after the calculus has been presented, so you're gonna see, but it's an excellent question. Okay, so these do the things that you expect them to do. It's not, I don't really have to explain to you what the kind of algebraic properties that this thing has, because apart from like edge cases, this is exactly what you studied maybe in primary school, like I'm not gonna say even high school, right? This also explains why I'm taking this. Oh my God. Yeah, let me go first here. It's like there's a whole like universe of these structures that you can contemplate on the reals, right? And specifically, like the two most common ones, apart from the vertical axis, which is about like considering only half of the reals in some sense. But the other axis is where you see like another possible choice of this structure, which is instead of taking the positive reals with the multiplicative structure as the primary one, you take all the reals minus infinity infinity, and instead of multiplication, you consider addition. Okay. And these are isomorphic. Okay, these are isomorphic. I call this an apparent duality because, of course, this is taking logarithm in on the one hand and taking exponentials on the other hand. But the difference is here, the three generations of connectives are a bit less intuitive. Just for starters, the multiplicatives are the additions, which is confusing on just to say. And then the additives become these operations called log sum exp. So you would have that A plus B in that sense would be the logarithm of the exponential of A plus the exponential of B. Okay. And in fact, it's a property of a thing called log semirings, which are semirings with a logarithm that does exactly what you expect, that you can sort of produce like an infinity of structures because you can always like shift up and down. There's like an infinite ladder of things that distribute over the one before, and you can use the log to move along. And these are all isomorphic choices in this case. So in fact, I could go on with this diagram, right, in both directions. But I prefer to keep this one because it's just easier to present, okay? But if you see something, you're like, oh, well, there should be really a plus here, not a times. Try to think. You just taking an isomorphic choice moving across this diagram. Okay. So specifically, Lawvere works here, right? Famously in his paper on metric spaces as generalized, as enriched categories. He works in this enrichment base. Okay. I work here, but it's not a big deal. Maybe a bigger deal,
Which way is your ordering?
the usual way, like the.
Sorry, I didn't see the ops on the left hand, the right hand.
Mhm. Um, what was I saying? Oh, right. So in the other axis that I ignored so far, you see maybe a more conspicuous choice, which is, do you want to consider all the reals in a certain sense or half of them, right? So very often people restrict to just half of them, usually the positive half, okay? Because it's just more intuitive, right? But many formal properties of the logic actually depend on having the negatives as well, okay? For instance, there is this work of Bacci, Mardare, Panangadan, and Plotkin. It's a series of work where they develop a logic. I'm not going to say a quantitative logic value here. It's not quantitative in the sense that I presented at the beginning, but it's a logic about that quantile. They call the Lawvere quantile. And they take only half, right? Because they don't use the negatives. And you can see that that choices break some nice properties of the logic. Basically, because when you negate something, you lose information. So when you negate twice, when you negate once already lose information. When you negate twice, it's even worse. Okay. So for example, this breaks completeness for them. And so they only have completeness for a very restricted class of theories, which is fine. We don't have completeness at all. So, but we don't have that problem, for example. Or another famous case of limiting yourself is probability theory that happens here.
You don't have completeness not because you can't prove it, but because you can't formulate it yet. Is that right?
No, we can formulate it. No, it's not even not true. We just didn't manage to prove it yet.
Oh, okay.
My belief is that it is complete over the reals, but I don't yet know how to prove that exactly. So probability theory happens in the negative multiplicative reals, right? So we always say something is between 0 and 1. And there is a good reason why it's between 0 and 1, which brings me to my previous slide, which is, can we interpret the positive reals as actual true values? Let's say like in a conceptual sense. I think this is a necessary thing to talk about because otherwise it's not clear what you mean when you say this sequent is valued 3, right? And so this is an interpretation that is very classical in the sense that we think of real numbers as like degrees of beliefs. Now, I call them here ratios of beliefs because that's more accurate. So specifically, we start by saying that 1, which is exactly like the middle of the positive reals, means that I'm indifferent to something. Okay, so if I judge a fact as 1, it means that I have no evidence either way to say that I really believe it or I don't believe it. And then all the other things are comparatives, right? I never say, oh, I believe this much. It's always I believe this twice as much as this other thing, right? Possibly twice as much as the thing I'm indifferent to, right? Which is like the neutral state of affairs. So 0 and infinity are your certainty and your impossibility. When you negate, so when you take the star, you mean that instead of being confident that something is very true, you are dubious, right? So it's a negative kind of belief. And then you have the classical ways of combining beliefs, which is like the additive and the multiplicative ways. So when you have one fact and you have two different reasons to believe it, one that would bring you to believe it A and one that would bring you to believe it B, then you can add those things together and say, I believe this fact A plus B, right? So this comes, for example, in the disjunction of events in probability theory, right? So I have an event and I have two different reasons to believe it happens. One is given by one side of the disjunction, one is given by the other side. And so you sum the probabilities. Whereas when you take the conjunctive multiplication, so when you multiply basically, you give a multiplicative interpretation of this fact, and you say my fact actually decomposes as two different facts. One which I believe A, which I believe B. Okay. So for example, the fact that it rains and it's sunny decomposes as two facts, and I assign the belief of the conjunction based on how I believe each of these two facts. Okay. All right. So this is my attempt to give a satisfying semantics to this.
Where does the p sum sort of appear?
Oh, yeah, that's a good question. So p sum, so the p go to modify this, right? And specifically, so I don't have a good interpretation of like a specific p, but I can tell you what it means to vary your p, right? So as you go from 0 to infinity, the larger your p is, the less democratic you are when you combine these two reasons in believing A and B. Okay, so the bigger P is, the bigger the weight you're gonna put on the one reason that is larger than the other one comparatively. Okay, so instead of being like, I don't know if it's A or B, it's probably both. Hmm?
Is that one?
Yeah.
I don't know the difference between I'm not, I don't know.
Plus normal plus is P equal 1, right? As you grow, then you get more and more, like you want to look at the stronger reason you have to believe about this fact. Okay. Until you get to infinity where you have just the maximum, right? So I'm gonna believe this fact based on the strongest evidence, and I'm gonna ignore the other pieces of evidence that I have, right? Yeah. Yeah.
In the usual interpretation of probability, which corresponds to the multiplicatively negative reals, right, between 0 and 1,
Yeah.
one gets interpreted as certain.
Right.
How do I square that with the idea here that one means I'm indifferent and
Yeah.
that infinity is certainty?
That's a good question. The point is that in probability, you always talk about your ratio. It's like your belief compared, like, how do you say it? Like you have a baseline belief, which is usually implicit, which is that something in your like universe of events is gonna happen, right? And so you assign to that probability 1. You say, assume that this is your basic thing, right? So everything that has the same probability as that is something I'm indifferent to, right? Because I know this is exactly as believable as the thing I already assumed, right? Whereas all the other events are judged compared to this initial assumption of this universe of events is going to happen. So how likely it is that something is going to happen, given that something within this universe is going to happen, right? So if I say 0, then I know that it's completely unlikely that will happen. If I give 1, it's as likely as the thing that I started with.
So in this picture, I would be picking, there's something I am 8 times more confident in than baseline, or say, but now I make that certain. And so I scale everything relative to that. I might as well have chosen that originally to be 1. So it's no longer that I'm indifferent to it, but it's just that I have that thing. But since I'm scaling relative to it, I don't care what its scale is. And now I'm just giving you a ratio, and I'm giving you the dubiousness I have with respect to that fixed thing. My fixed belief being something from my sample space will happen.
Yeah. Yeah.
And then for my second
Precisely.
question,
Precisely.
That sense, it makes sense that in the proof theory, you also want your hypothesis and so on to also be quantitative. Right?
Yeah.
I was thinking this might be like, or one way to think about it is like, these are the odds you would give on something
Yeah.
happening, but that sort of doesn't behave in that way, right? Because like, if I say like 1 is my benchmark for certainty or something, and 0.5 is like, I can believe something's twice as likely to be true in the sense that I could it double the odds, and yet still not think it's certain even.
But so
So
like
these are more like answers.
Well, I was thinking that, but then what you said makes, so you're saying you could like, if you just say true is 1, then you can still work within that and everything else is some fraction of that. But like something which has a probability of half, I might say I believe this other thing twice as much in the sense that I would give double the odds in that happening. But that's not the same as saying I believe it 1 if I've already said 1. It's like certainty.
I think so. It's certainty when you are in the probabilistic frame of reference, right? So because in a probabilistic frame of reference, everything like all your hypotheticals are sort of nested, right? It's like conditional probability is something like given A, what is the probability of B, and implicit is like with respect to A, right? It's this given, and whereas here you could in principle do something that in probability you never do because you wouldn't get normalized probabilities, which is take the odds, right? How much do I believe this fact compared to this other fact? Like, and so these are odds, right? So if you have your atomic propositions be your events, and you value them given without probability or any actually function that tells you like how much you believe them, then the ratios of these are the odds, right? In the classical sense. So these are odds in a sense.
Right.
So even odds are like a specific like kind of semantics, right?
The thing you said before, where where you pick something that you're going to believe, the way that you interpret these as odds is by, or the way that you get that gives you probability, but you also form the odds by considering it as odds relative to that thing. Is that right? Or is that wrong?
I got a bit lost in the references.
So like if I say like it has 1 in 100 odds, I mean that the probability is 1 over 100. And if I started with on the other hand, that's the same thing as dividing by 100, my first number.
Yeah.
So
If you say 1 in
yeah,
100,
even.
you mean that you believe the second thing 100 less or 100 more, I never remember than the first thing, right? So it's that kind of judgment, right? Which is what you're doing here, right? Except that here, like in principle, like these beliefs are just beliefs, right? They don't have to be about like specific events or obeying like some theories of probability. I have a little pet peeve with probability theory used as a theory of epistemics because it's like there's a lot of like subtleties like this that are not usually talked about. Like the fact that you assume there is like a totality of things that can happen, like that's already a big assumption, right? Things like this.
Right, like I don't see complements like here, whereas like in probability.
Yeah, exactly. Yeah. That's a big point. Like, yes, you don't have complementarity here. Unless you restrict yourself to totality, in which case it arises from that assumption. It's not something about the way you're doing like the reasoning, right? It's about this assumption of totality that you have in the first place. Okay, let's go on. So I'm gonna present you the propositional fragment first. So this is based on a notion that we call, I say we because I'm developing this with Bob Atkey and Katya Komendantskaya, Charles Grellois. I should have said that at the beginning. So these quantitative calculi that we're working on are basically proof calculi. In our case, going to be sequent calculi that happen in this meta theory of the positive reals as a Lethic value. Okay. So what does this mean is that if your judgments, specifically your hypothetical judgments, are going to be real values, then also the way you combine them has to be a kind of operation, right? of reals. So specifically, usually in things like sequent calculi, you have, right? You do things like this, and then here you might have a different sequent. Okay. And implicitly, you have in this white space, you have something like and, right? This is what it means to have two sequences. And you basically only say that. You could be putting ors there, but the point is that to put ors is the same thing as having two separate rules at that point, right? So you don't, but you could, right? And that's also what you mean. So what happens when you go from the Booleans to the reals? Well, now you have to be explicit about that because there's many options about what you can put there, right? So here's a combinatorial definition of what your rules even look like in such a calculus. It's a bit pedantic, but the point is that a rule is going to be a bunch of sequence. It's going to be a big fraction, and on top you're going to have a bunch of sequence, and these sequence are combined by these red operations here, right? Which are the operations that we've seen before. Also, I could have one of these constants, which is something that we need later. And then once I combine them, I conclude something here. Okay. So here you're going to have some connective, connective, connective.
Version, yeah.
Yeah.
Here you've listed P and negative P separately.
Yeah.
Is that P a symbol? Or is that a number?
Yeah, that's part of the language.
So it's not like, that's not standing in for
That's a meta
real number. That's a symbol.
No,
That's
it's a meta real
a
number.
meta real number. So why can't I just put a negative one?
Yeah. Like, why can't you just have H plus P H and allow for like -1 as a possible P?
Right.
You can. The reason I'm doing that is that in the first order it actually makes a difference. So -0 and +0 will be different. In this case, it actually doesn't. In this case, I could have just said there's that.
In the first order, -0, +0.
Yeah. So I like to distinguish them conceptually. That's basically the reason.
Instead of additive. You just don't want to have to keep saying, oh, for negative P, it's this.
Yeah.
Why don't you have to put in like tensor star?
That's a good question. I don't really have a good answer to. Like, I'm gonna show this the calculus now, and you can see it's like no good place. Yeah. So
Sorry, so is P not allowed to be 0? Is that what?
it's not allowed to be 0. But you could allow it to be 0, but it's just it degenerates at 0. So it's just like infinity for positive and 0 for the other one. All right. Sorry. Anyway, so okay, so you have these rules in which the top row is just a bunch of sequence combined by these red connectives. And then the way you combine rules is basically the same, except that now your trees have like this typing in the way they can branch. And so you have to you have to bring with you all these connectives. So if you have a rule like this, and then you're given like derivations for each of the structures of sequence, then you get a new derivation, which you obtain by combining the entire derivations. Okay. Right. And let me say another thing. So there's a special status to those rules whose top row is in fact just a constant, meaning it doesn't involve any sequent, but it's only constants possibly combined by other connectives. Okay. And as you might guess, those are your axioms basically, right? In the sense that it can start from something which doesn't presuppose anything else. And let me also emphasize that 0 is a valid choice, right? This is also something you don't usually do in logic, but it's perfectly fine because if you start from false, you can derive everything. that's okay, but you still started from false. So, so as we're gonna see later, this brings us to the concept of validity, okay? So whereas in sequent calculus, in the usual case, if you have a proof, and that's a valid proof. Here we have to distinguish two things. First of all, what is an invalid proof? But actually, we just have to distinguish between like the various degrees of truth, right? Of all these proofs that I get. So the fact I can write a proof doesn't mean that the sequent I get at the bottom is true, right? I have to tell you how much does that proof corroborate the sequent that I get at the end, right? And the idea is that as you build a proof, so well, first of all, a proof is a derivation where the top row that I get as just is a closed structure of sequence. Okay, so there's no sequence appearing on top. Okay, so it's gonna be something like 1 plus p1 tensor infinity. Okay, something like this. And then here we're gonna have
This way, right?
you can get every real number this way. Yeah.
Or, well,
Do you have like
Well, if p is all real numbers, yes.
okay.
If you limit yourself, yeah, yeah.
you have that proofs are monotonically increasing in the sense that at each step of a valid derivation, the likelihood of the things you're proving is never going down.
Yeah, yeah, correct. Yeah.
So it's just
Yeah, I should say like a rule is sound when it's like you cannot really say at this level, but a rule is sound when the degree of truth of the top row is less than the degree of truth of the bottom row, right? Anyway, so you have a derivation that starts from constants like that and ends with some sequent. That's a proof of that sequent. And you take the validity of the proof is the basically the evaluation of this expression in the reals, okay? So you can take this to be a syntactic object you evaluate, or you can take that to be like exactly the real value that you wrote down. Yeah.
question I had on the previous page, but it relates here, is do you have the quotient out by the, like implicitly, the invisible and is associative in the usual sequent calculus, right? Do you have that quotient out by any of the relations?
All of those relations are admissible rules.
Cool. That's
right? It's pretty cool. So you don't have to, which is nice. So also, if any of you know what hypersequence are, you don't, then I won't make this point. But these are not hypersequence. It's exactly in that sense that all the structure rules are admissible. You don't have to put them in. Okay, so you have a proof. The top thing is the validity of the proof. So it's basically how much gas you put in the proof in terms of truth value, right? So this solves the problem of starting with zeros, by the way, right? If you're worried about that, because you start with 0, you can do whatever you like here. You get to your sequent, but this proof has validity 0, okay? So it is a proof. It doesn't count. Specifically, then we can say, okay, give me a sequent. Look at all the possible proofs of that sequent, like in the combinatorial sense, okay? So look at all the possible trees you can build. Look at the top of everything. Give me the biggest one. The biggest one is the provability of that. So how much you actually need, like, or like how efficient you can actually be at proving that sequent. So clearly all the proofs of validity 0 for that sequent do not count, okay, because they are 0, unless the sequent is actually not provable, in which case its probability is 0 because it only has proofs of validity 0, okay? And this is completely analogous, by the way, to the definition of provability in the usual sense, right? All these definitions are the usual definitions in the meta theory of the reals, right? So for the usual thing will be there exists a proof of that which is valid, okay? So the validity usually it is valid, it is not valid, okay? And this also means that this is like as decidable as the usual notion of probability in the sense that if you have a proof, then that gives you a lower bound. It is like, which is in the usual case enough, because if you have a lower bound of a valid proof, then you know that you're done. In this case, just tell you, well, it's at least that provable. And then you need some extra results about your calculus to be able to say, well, I actually can compute the probability of something, right? So in our case, the such a result would be there is a normal, like sorry, there's a finite amount of like normal form proofs that I have to check. And so that supremum is actually a maximum, right? So that means I can decide like the probability of this thing. Okay.
A question.
Yeah.
About this, in the doxastic interpretation you gave before, how do I understand the validity and probability? Like I know that the provability, right? It's a number. So do I interpret that as the sort of ratio of my belief in the provability of the sequent, or in the truth of the sequent, right?
Not exactly. So these proofs are me reasoning about my own beliefs, okay? Specifically about the belief I have in the right hand side of a sequent compared to the left hand side, right? So I have, well, I can just show you the rules because it's just like it's just easier. So I don't know where can we begin?
We'll just go through the rules now, and then
Yeah, okay. But I mean, so the first slide of the rules is like, oh, well, so QLL, by the way, is like specific quantitative calculus that's quantitative linear logic, okay? The idea being that, yeah, this wants to be like linear logic. So these are the structural rules, really easy. You have exchange on both sides. You have axiom, that is a rule with validity 1. And you have cut, which is a multiplicative rule, meaning there is a tensor there. Easy. The multiplicative fragment is also completely analogous to the usual one. In fact, if you remove the red bits, this is exactly multiplicative linear logic, with the exception of this fact that our unit for tensor and our unit for par are the same. Okay, so this is called an isomix linear logic in the categorical semantics literature, at least. Okay, so specifically, this implies that we have a rule that's called mix. That allows us to like directly combine two sequences. This is derivable from cut. Okay. So this mix rule is discussed in linear logic already. Isomix means that you get it by cutting one. Okay. Because here I can introduce one on the left and can introduce one on the right. So I can cut it. All right. So far, nothing new. Well, we can already see, like to answer David's question, like the way, for example, that one would like see the interpretation that I gave at the beginning, the Doxastic interpretation, as like be incorporated in this calculus, right? So here's a piece of evidence that I believe A and delta a certain degree compared to gamma. Same thing on the right. If I put these two facts together, I get their product.
And then
Okay.
when you got that interpretation, at the meta level, the multiplicative, I believe this multiplicative thing.
Exactly.
Because I believe this meta multiplicatively, which is to say, like, at the same time.
Yeah. It's like these judgment decomposes into things. So it's made of two pieces rather than the other thing. Okay. It's holding up so far. Let's see. When it comes to the additive fragment, this is probably the most different one. So you can see, let's see. So these rules are 1 and 2. These are, again, basically the same as the one you would find in linear logic for the additives. Specifically, sorry, it's these ones on top. Okay, so if you replace the red connective with emptiness, then you get the left introduction for plus and the right introduction rule for with, if I remember correctly the names. the ones below are the ones you wouldn't find written like this. You would get these rules split in half, right? So you would get given, you would split them like this or like this. And so you have two different rules, right? And same here. So what is the difference basically is that here I cannot just I cannot prove the entirety of the bottom thing with only one of those two, but I need to combine their truth value, right? So the limit case is when p is infinity, in which case one does indeed suffice, and so you can prove that this single rule is in fact interderivable or interadmissible with the pair of rules that you have classically.
So as p goes to infinity,
Yeah,
the top plus becomes an and again,
comes an or.
right?
So
The top row.
Plus p is an or, and plus
Right,
minus p
right.
becomes an and.
Yeah. So the top row
Yeah,
becomes an and.
exactly.
And that's why that you see them in that form with both things at the top and the middle. The
Exactly.
bottom one becomes an or,
Exactly.
which we discharge the mapping property of to give two separate rules.
Yeah.
It's really, really cool.
Yeah. So the result is that if you have a formula in mul and you reason about it using the infinity fragment of this, so where all the p's are actually infinities, then this is conservative or mul. I believe is also adequate, so cannot prove new things. I'm pretty sure that you can prove mul things. So at infinity, this is the same exact calculus, all right? Specifically, so where you have to cut truth at one. So you say, well, if my probability is greater than one, I like this to be the same as saying that this is provable in mul. Okay, this is QLL. So this certainly holds, and I'm confident the other one holds too, but I didn't prove it yet. Yeah, and then you have the additive identities. So you have x falso quad libet that just is an invalid proof for any sequent. And that's the same thing as right rule for bottom and left rule for top. And then you have these infinity rules. They're like, if you are certain something is false, then everything goes. And same on the other side. If you're certain about something, then no matter what I assume, I'm just certain about it. Let me also say, so again, this is like quantitative mul. So you can think of this also in terms of resources. So the usual interpretation of mul in terms of resources is a sequent is a convertibility assertion, right? If I have,
Sorry, what's
yeah. Sorry, it's multiplicative additive linear logic.
Okay.
So it's linear logic without the exponentials, right?
So you need the two ones, right? Or I guess.
Yeah, good point. Yeah, this is isomul, isomixed law, mul. Yeah. Like certainly you can prove something in mul. Like this direction doesn't need that, right? This other is fine. Thanks. So okay, you have this convertibility interpretation. The sequent is saying, well, the resources on the left can be converted to the resources on the right without waste and without creating anything from nothing, right? Here you have the same, except now the sequent, instead of giving you a convertibility assertion, it gives you a conversion rate, right? So it's the rate at which the things on the right can be produced by the things on the left, okay? So for example, if you say, well, I have €1 and this gives me a pizza, and you say, well, this is, I believe this five. I'm so used to say phi that I lost the number 5. Wow. And now you can say, well, my beer instead is cost 4. Then you can ask, if I want a pizza and a beer, how much will it cost? Well, I can apply this rule here, right? And that tells me, well, it's gonna cost pizza plus beer euros. which specifically, so the red thing tells me I have to add this thing, and indeed I get 9, which is 5 plus 4, right? Nothing impressive, but it's just like this brings all.
Oh, I see. The idea is that we can convert euros into pizza at a rate of 5 and beer into euros into beer at a rate of 4. And so I can convert euros into pizza and beer at a rate of 9.
Yeah.
One thing of pizza and
Yeah, so compared to the same
But
thing.
here, so going back to the doxastic thing, is that you're assuming your baseline belief about what you can get pizza and beer for?
Well, yeah, so this is a different interpretation, but you can say, well, I can interpret this as saying, so in the belief sense, as saying, well, how much can I convert the belief I have in something into the belief I have in something else, right? So my belief in pizza doesn't make a lot of sense, but if you put here like, oh, I witnessed some event omega, and then I have some other event omega 2, then I can interpret this as the odds of omega 2 to omega 1. So how much belief do I put in omega 2 compared to the belief I put in omega 1, right? Just like some sort of convertibility between events, whatever that means.
So when you're doing the resource ratio interpretation, can I try and say that again and see if it's the idea is that there's a resource interpretation of linear logic, but that's possibilistic. It's whether you can convert these resources into these other resources. Since that's because the truth values for the judgments are Boolean there, in other words, possibilities.
Yeah.
For you, they are now numbers, and you interpret them as ratios. And you interpret them as the ratio of conversion of units of a resource and the left, the units of the resources.
Yeah.
And then you have these.
Yeah. And notice it's a bit weird because like this plus, now it's an additive. But usually additive is I either have one of the two, I don't have both, right? Whereas here is I have them both, but in a different sense, right? I have them both compared to 1. So one mind-bending thing about this logic is that your notion of additivity is relative to your meta notion of additivity, right? So your plus, in the usual meta theory, it's not an additive connective, right? Because it's not idempotent. But in this case, since we assume that plus is already a connective in the meta theory, now we're defining additives in terms of that, right? And so or P and P are additives compared like relative to the choice of additive that I made at the meta level, right? And so everything works. Okay.
With the ratio interpretation, we should try and make sure things are making sense. If I had like 2 or infinity tends out to be or
How much do you believe in beer? So this has to be 0 necessarily, right? Well, unless beer is infinity, in which case it's 1. This is philosophically thorny territory.
I think about it in the other way, like where I'd say like €1, from €1 I infer beer, like a fifth, that sort of feels natural, and then I'm using the -1 plus conjunction.
What do you mean? Like it's like I put beer on the left.
Oh no, 1 on the left. And I say, well, with €1 I can buy a fifth of a, there's a 20% chance I'll get a beer out of that.
I like this. the lottery interpretation.
And the 25 or 1 on 4 on the right.
And
then I'm doing a plus to the -1 on top.
Well, then you would have, so instead of 1, we put something else here, like 2.
Can I not have if I have I mean the red connective, can I not just have that?
Well, it can also be the same, yeah. It can also be the same. So for the red connective, sorry, I think you want to apply this rule here.
The top right one, yeah.
So here you would have harmonic sum, and here you would get you still get one, yeah. Now this is pizza plus star beer equals 1/9.
Mm.
Yeah. Now what this means, we need to go through some convolutions.
But I guess that's like the conversion rate from euros to pizza plus beers. In another sense. I mean, it's just the reciprocal of the thing.
Yeah.
So.
Yeah, nice thing about harmonic sum of fractions is that you can just sum the denominator. Those sort of tricks. Okay. It's late. What do you want to do? I have
I
a
like hearing it. I don't know.
We can go for like 10 more minutes. I think we started a bit late.
So I have a quick question.
Go
Since
ahead.
I've seen that we don't have more rules down the slides.
No.
So we are not using an exponential model.
Yeah, I should come back to that question. So I don't know how to do exponentials. I have ideas, but I don't know. Because so an exponential should be something that like you would have something graded by p, and that bank PA should be like p idempotent, right? So it should be idempotent to a certain degree that depends on p. Okay, that's the idea. And at infinity, that like recovers like the actual hard things. So the weird thing about these exponentials is that they turn additives into something which is more additive rather than multiplicatives into additives, right? So I don't know if this is the correct interpretation of this thing, right? Or maybe there should be another kind of exponential, which is more like an exponential, well, a logarithm that turns multiplicatives into additives, right?
Because
TBD.
yeah, it would be good to see if there is a sense in which, I guess, having this ratio resource interpretation might suggest what might be a good notion where you have form of dereliction and so on, right?
Mhm.
Yeah. About it, yeah.
Yeah.
Wouldn't the naive interpretation of the bang, if you take the linear logic interpretation in vector spaces where the bang is like the box space, I think that's right, then that would be 1/1 minus x.
So the naive interpretation gives you the geometric sum of something for one and like the reciprocal of that for the other one. I don't know what that means. So yeah, that's TBD. But I think it's really interesting as an idea. Also because like you can define it's like it really behaves well in the sense of geometric sums. It's like even at the limit, it gives you what you think should be in the limit. Uh, so it's like nice arithmetically speaking, but then it doesn't really do the thing that an exponential does because it doesn't actually turn multiplicatives into additives. So that I don't know. At some point I stopped and be like, mal is nice. Mal is good. So here I wanted to give you an example of a proof you can do, or like many proofs even. So this is a very like important thing from the point of view of the machine learning applications, which is that you want to prove this thing here, right? So as we said, our yeah, p-sum and harmonic p-sum are not idempotent, right? So this is idempotency of harmonic p-sum. Okay, this doesn't hold. The other one holds, like holds one. Okay. Sorry, well, holds to some degree. This one doesn't hold, and it holds less than one. Okay. But nonetheless, within the scope of the calculus, it is a thing you can reason about. Specifically, you can prove this, and the proof is going to tell you like how much does this actually hold, right? So you can do this by saying this is now by in a very simple way. So I apply NP, right? And then now I have two axioms, right? So again, these get combined all at once. And so you get that this sequent here holds 2 to the minus 1 over p, okay? So we know that this is like the degree of idempotency of NP. So why did I say this is important? It's because, as you can see, you can reason about this as if it was just idempotent, right? So you do have a proof of this. It's just that this proof comes with a certain like validity it has, which is not infinity, but it's something. So you can sort of keep track of how much are you actually using the assumption that this thing is idempotent as you do the things. And why is idempotency an interesting property for machine learning? It's because there is a very cool theorem by, I would love to remember the name of these people, I just don't remember. I'm sorry. There's a theorem by these people that do differential logic that says on the reals you can choose two of these properties for a connective. So either is idempotent or it's associative, or it has smooth monotonicity, which means that if you take the derivatives of its components, they are positive, right? Yeah, positive. What does that mean? It means that if I increase a little bit one of its component, right, one of its arguments, then I get an actual increase, and that increase is differentially relevant, okay? So there's this theorem that says, well, such a thing doesn't exist. You have to pick two, right? So in this case, the choice we make is we say we pick these two. So we have connectives like harmonic p-sum or harmonic sum that are smooth monotone and associativity, but they're not idempotent. And so the way we fix idempotency is in this way. So the real way is by embracing this idea that these are additives relative to the meta theory of the reals. And notice how like basically the additivity now reduced to tensor, which is multiplication, distributes over these things, right? This is what it boils down to. So we do this maneuver, and then idempotency is recovered in this like partial or quantitative way. Okay. And yeah, apparently this works very well. Like there's a guy who is implementing this logic for an N verification, and apparently this property is crucial to have like good properties in verifying that, well, in training models to verify some spec by construction, basically, right? So instead of verifying them later, you train them with a certain quantitative predicate. And if you write it using these connectives, since they have property 3, the gradients actually are informative for the model to learn to satisfy the property, right? So that's it, right? What else I can say? I don't think we have time for much more. I'm gonna just say there is a cat elimination theorem we're working on for this logic, which seems to be just working fine.
What theorem?
Cat elimination. Okay. So this is what gives us the result that I mentioned before, that in practice you just have to check finitely many proofs of a given sequent to know its provability. And the reason, yeah, because you have finitely many cut-free proof of a thing. Yeah, and there's like some interesting proof theoretical properties that arise from there. For example, yeah, there's a specific case in cut elimination in which you have to basically resolve a cut of this kind, right? So in our case, this would be a tensor. And now a very subtle fact is that in if you have two proofs here, then in fact these two proofs alone suffice to prove this thing. So when you eliminate the cut in this calculus, you actually see this in terms of you literally, like the naive thing you do, gives you as a conclusion this sequent plus this sequent again. Okay, so you conclude it twice. And so you can prove, in fact, that there is a, as I said before, like basically all the structural rules that you would expect at the level of the structure of sequence are admissible. You don't have to assume them. And there is also a case of this here in which you can show that the rule that takes the average of these two things, so here would have like you can put, well, let's put P, it doesn't really matter. So you have this, right? So you can have this rule here. So these are all red stuff, red things, right? Right, so you have two branches of this proof. Both are proving the same thing. And a rule like this is basically saying you don't have to choose. You can take the average, and this gives you a proof of your sequent, right? And this is just admissible, so you don't have to assume this in the calculus, right?
Sorry, the 2 to the 1 on P tensor thing, P plus A to A is admissible? Or?
Yeah, sorry, I got a bit. So
That's because if you put ones in, right, you'd have this scale.
Yeah,
You're rescaling the top end to one.
Yeah. So like the easy thing would be to say, if I have, oh, sorry, it was minus 1p, so this is 1/2, right? So take half of the sum of two things intuitively, you get the thing, right? So here, the point is that here I can have very different proofs, and I can just take their average in a sense, right? So even if you don't actually take the average, because there's no notion of average of the combinatorial objects that are the proofs, the facility of the language somehow still see this, like, and so you have this idea in which apparently in proof theory is very interesting, like proof theoretically speaking, that you have a kind of superposition principle for proofs of things. So rather than having to choose branches as you do your proof, you just do everything at the same time. And these various proofs end up sort of not interfering because we're not doing quantum mechanics, but they like add up together to give the proof of the thing you're trying to prove at the end, right? So even compared to other calculi, this is interesting in the sense that it has way less non-determinism in things, in the choice of proofs, in the choice of proof transformations, for example, during cat elimination, because you keep everything around at once. So in a sense, it's a bit of a cheat, right? But it makes things a bit more smooth. Okay. I think I'll end up here.
Okay, great. Let's thank Matteo for his.
Thank you for listening.
Are there any questions?
So many.
This is really cool.
We can do part 2. Thank you.
Yeah, I noticed we're like
Thank you.
almost halfway through the slides, so maybe.
Yeah, there's the whole, well, there's the algebraic semantics we didn't touch on. which are soft tiles. Yeah, I really like the name.
Wow.
So the conjecture is that there is actually only one soft tile, which is the reals. That's our completeness conjecture at the moment. And then there's all the first order thing, which Jose knows a bit about, I think. But yeah.
One of the I think like really deep observations you've made here is that the meta conjunction involved in the top of the rules in linear logic is not always the multiplicative conjunction, sometimes it's the additive conjunction.
That's interesting, yeah.
And that, I wonder how that relates to your what you're saying about these proof search properties and stuff. Because that's the one that appears when you eliminate the additives.
Yeah.
That's really, I think that's really cool.
It's fascinating, yeah.
I have not seen that I'm super deep in this stuff, but it's very, very cool.
This is the calculus, by the way, yeah.
And the fact that when you take P equals infinity, you end up with the top interprets as a Boolean conjunction, but the bottom there also interprets as a Boolean conjunction. So
yeah,
that's like really special.
Yeah, that's the really fascinating bit, I think. Right?
Yeah, very, very sad.
There's like an ulterior level of analysis of this connectives. Yeah.
It suggests a difference in the proof search, right, between how you're as you said in the doxastic interpretation, you have to believe for because it decomposes as this, which appears in your multiplicatives and in cut, and then you have your belief for different reasons, right?
Yeah,
which suggests a sort of undetermined.
Yeah, and here, like the lack of the negative multiplicative as a red connective, it's very apparent that you don't need it, but I still don't completely understand why. You would think that would still be something that you see, right? But you don't have that.
So you didn't talk about, oh no, there's star. Never science. Could you maybe just put it in, but it just makes the tensor star appears on the other side. Like you flip the right. It's kind of stupid to do this, but you put the meta tensor star and then you put the object level tensor star in at the other side.
Sorry, the other side of what?
Like, if you put the meta tensor star in for the object level tensor star rules. Oh no, doesn't work. Yeah, it's interesting.
Yeah.
I might stop the recording there just because we've gone on quite long, but we can continue this discussion in a coffee. Let's thank Matteo again.
Thank you.